Okay, Assalamualaikum and a good morning. So we'll continue with our lecture from yesterday. So go to the board, sorry, the notes. Okay, I believe somewhere around here we talk about essentially how waves propagate inside a particular initial frame. Let me just check. So let's go back here. So we come to the point of describing plane wave inside your initial frames in special relativity, and then we are going to look at the behavior of this propagation of light in the in a frame which has a velocity with respect to another frame. So we have actually considered the case where your O dash frame is actually being boosted in the x direction. So we're going to have this Lorentz transformation onto the wave vector that we have actually discussed before. And I think we have come to the point of showing you some relationship between the omega. Omega, remember, is the fourth component of your wave vector. So essentially that will change when you have your moving frame with respect to another stationary frame. Okay, so and we have come to the point of actually showing you this general Doppler shift. Okay, so remember your O dash over here is moving with respect to O. So your O dash has a frame here which has velocity v. Okay, and then the other thing that one has to remember that your k will be in some certain direction. Okay, so we'll see in a minute when we look at the other equation over here. So here is the case where remember we have this cos theta coming in from the propagation of your light with respect to certain axis, in this case in the x-axis. So over here, what's happening over here is essentially we have just like before, we have your O dash moving in some direction x, okay, and then we set the case of theta equals 0. So in other words, the light is actually propagating the same direction as your your frame O dash. Okay, so this k will be observed by both O, which is considered stationary, and your O dash, which is going to be moving. Okay, so your omega over here is the one observed by O, and then omega dash is going to be observed by your O dash. Okay, and from this particular relation, we'll get that you have this gamma omega, and then cos theta will be 1, cos theta equals 0, and then you have essentially your omega is given by multiplication by some factor, which is essentially your your k factor with this replacement. Okay, and you can also consider the case of where theta equals to pi. That means essentially what's going to happen over here is that here's the propagation of your light, and then your frame is actually moving with respect to O in this direction. So that will actually give you just replacing your v over here by minus v, and essentially we get this. Okay. So I think we did another thing. We did this particular case. Okay. Here we are just inverting the equation that we had earlier from here. So to invert omega and omega dash, okay. So the easiest thing to do it, I mean, you can do it algebraically, but then the easiest thing to do is essentially to think of your frame O essentially moving with respect to O dash in this particular case, as if it's moving in the opposite direction. Okay, so this is minus V. So one can just simply replace that formula star before by just replacing it by minus V in the formula, and then you get this particular plus. Okay, so this is the inverse transformation from O dash to O. Okay. And let's use this formula and look at the case where your theta dash, okay, this particular this theta dash is actually pi over 2. So you have to remember in this particular case, let me see on the diagram here, just it will be something like this. Okay, so your O dash is your O dash is moving, sorry, okay, we can take O dash to be moving in the same direction as your light in this case, and then essentially your O is moving orthogonal to it. Okay, and then what happens in this particular case, then you set your theta dash equals to pi over 2, and that gives you 0 here, so you just have your omega dash or omega equals to gamma omega dash, or omega dash equals to omega over gamma. Okay, so this is essentially what we call the transverse Doppler effect. Okay. I think we stop at that particular point. Checking. Okay. So the other thing that we also did yesterday before stopping, I think we just mentioned this. Just remember that your tau is the periodicity of your wave, which is actually given by 2 pi over omega. Okay, so in this particular case, then you just simply invert this equation, for example, or this equation, whichever. Okay, and then you get by using the reciprocal, really, you get your tau dash, which is a periodicity of the wave oscillation, okay, as equals to the gamma times the periodicity in the other coordinate system, which is in this case your O over here. So this you can actually get from here. Okay. So you just simply use this particular formula to get this. Okay. So the next thing that we want to see is how the specific components of your K is related to this Doppler shift. So we're going to set this components of your K mu dash, for example, inside this transformation of your 4-wave vector. So you set your mu dash equals to 1 dash, for example. So this is just your x dash component. So essentially, remember the Lorentz transformation that we are actually looking at is of this boost transformation, and the only non-trivial call elements here are just your first row and your fourth row, or first column and fourth column. Sorry. So and then you actually see that in that particular case you can just simply plug in all the components in. So you get gamma k1 minus gamma v on c k4. Okay, so remember this is your components of your k. And then if you just recall that earlier we had your v equals to v00. So v dot k is essentially vk1. vk1 the first component, okay, because the second component when dotted with this velocity vector here, it just give you 0, so you get vk1, and we're going to make use of this k1 here and sort of multiply v, and then and essentially we get this vk1 here. Let me just check with that. So that gives you K4 is actually your omega over C. So that gives us, let me just try to do this, gamma okay, let me just write this first. So gamma K1 equals to gamma omega on C cos theta. So gamma VK1 will be gamma oops, I don't want this. Let me just figure out we had that before. Sorry, I'm just figuring out what I missed. Cos theta using so I have omega over C over here. I'm confused now. Let me just check with the ones before. Omega V on C cos theta. That's VK1. But I get this thing figured out. Okay, let me cancel that. Well, okay, one's supposed to be able to get this equation from there. Just got confused a little bit. But essentially we need this factor. I will come back to this later on perhaps. And then essentially this equation is arising from that and this equation that we had earlier over here. Sorry about this. But I figure it. Okay, and essentially with that, one can simply rearrange this equation into this equation. Okay, and what we're going to do next is probably think of your k. Let's look at your k vector is k1, k2, k3 here, and what I'm going to do is to assume that okay, your signal is actually traveling in xy plane. So in other words, here's your o-axis with x and y here, and then essentially your light is this is supposed to be n. So this is y. So your light is actually traveling in this plane. So that's essentially your vector n. Okay, remember that your vector k is modulus k times n. Okay, so n is essentially the direction of propagation of your called light over here, and so that gives you these components. So your k is really now modulus k cos theta. So this is theta here, and modulus k sine theta, but your z component is 0. Okay, because we are assuming it to be traveling in some plane. Okay, and the plane is xy plane, so your z component is actually 0. So you have that. Okay, and because of your what you call your y component over here is actually perpendicular to the direction of your what you call direction of your frame moving with respect to O. So remember that O is actually moving with, sorry, O dash is moving velocity v here. So the components for your k4 vector along the orthogonal direction doesn't change. So in other words, this will stay the same in both frames. So you get remember that in your O dash will be k dash, of course, and k dash would be omega dash over c. You have to remember that okay, your k squared, because it's a null vector, okay, it's propagation of light, this equals 0. Okay, so you have in the O frame it will be k modulus k equals to omega over c. In your O dash frame will be k dash equals to omega dash over c. Okay, so in other words, we will have this component of your k2. Okay, second component will not change with respect to this direction of the O dash frame. Okay, so so you have these two equations now. So what one can do is essentially to remove the omega itself, okay, by no, just substituting your omega over omega dash over here, for example, and then you take your sine theta dash. So over here I can rearrange this to be sine theta dash equals to what you call omega over omega dash sine theta. Okay, so now what I can actually do is to divide sine theta dash by cos theta dash, and similarly on the other side, and then you get this formula for tangent theta dash, which is given by this. Okay, And if you simplify this with respect to this sine theta and cos theta, you get tangent theta times this square root 1 minus v squared on c squared divided by 1 minus v on c sine theta. Okay. So and this is actually the formula for the aberration that we have seen before when we discussed about Lorentz transformation before in the case of the kinematics, Lorentz kinematics lecture. I can't remember which lecture was that. Okay, so essentially we reproduce the formula for the aberration formula by just simply using the how the components of your K, which is now assumed to be in the xy plane, and then essentially we have that. Okay. Okay, let's move on. I will get back to this if we take a break a little bit and try to figure out that one. Okay, let's continue with this particular section of the lecture. This is another application of your Lorentz transformation. So one of the things that one should remember that for the case of the what you call fields, okay, all your objects, for example, your tensor, in this case, will be dependent on your coordinates. Okay, so in other words, if you have, say, this tensor, which is actually a rank mn tensor, okay, contravariant rank m, covariant rank n, and if this is actually defined in all points of the space, then it becomes a tensor field. So when it's a tensor field, it becomes functions of the coordinates. So what one can actually do is to take the derivative. Okay, so in this particular case, we take the derivative with respect to x alpha, and the notation, the shorthand notation one usually gets in relativity is by writing this as comma alpha. Okay, so and remember that earlier that we already mentioned here, your alpha, even though it appears on top in this derivative, okay, but the alpha is actually in the denominator, so your alpha will actually appear as a subscript, okay, lower index. So this will be the derivative. There's another notation which is going to be something like this, which I also use. So there are different notations. I hope when you see different books, you will be able to recognize. I think the other thing is the signature of your metric. So signature of metric in this particular case is plus plus minus. Okay. So you have to check whenever you read a different book, you have to check which metric signature that they are actually using. So, okay, so now the question is, okay, you have this object which has now more indices because of this derivative index. Okay, so one could ask whether this object is also a tensor or not. Okay, now one can simply do this. So we switch over to the dash coordinates, for example. So one has this partial derivative with respect to x alpha dash of the components of your tensor with respect to the dash coordinates. Okay, so the first thing that one knows that, okay, this is a tensor. So in other words, this will transform according to this line. So you have the Lorentz matrix m times, and then the inverse Lorentz matrix n times. Okay, contracting on these indices. Okay, but this one, how do we actually try to change this to your undashed coordinates? Well, you have your chain rule. Okay, so in other words, if I want to express partial partial over partial x alpha dash. Then by using chain rule is simply partial x beta partial x alpha dash times partial over partial x beta. Okay, so this is just simply chain rule. Okay, so once you have that, and then remember that what is this? This is just simply your inverse Lorentz matrix. Okay, so now I will just have this matrix multiplying on top of this derivative. The other thing that one should be remembering that your Lorentz matrix or the inverse Lorentz matrix doesn't depend on your coordinates. Okay, so like for the push case, it just depends on the velocity of the frame, or in terms of the rotation, for example, it's just rotational angles. So it doesn't depend on the coordinates of your frame. Okay, so in other words, this will only act on this tensor components, because this one is the one that depends on the coordinates. Okay, so one can just bring out all this Lorentz matrix and inverse Lorentz matrix outside, together with this one, which is now given by this inverse Lorentz matrix. So you have all this product of Lorentz matrices and inverse Lorentz matrices. Multiplying what? Multiplying this derivative acting on this tensor components. Okay. But if you look what this is, well, this is precisely the way how the derivative, okay, which is now written in terms of this, transform under what you call the Lorentz transformation. Okay, so in other words, this one is indeed a tensor. Okay, but this is only true in the case of special relativity, where your what you call transformation are simply given by this. Okay, and then of course you can have the inhomogeneous part. So, and this is essentially constant, and then when you take the derivative, you just get this Lorentz matrix out. So that's what's happening over here. If in general, what could actually happen, there's no, you have a nonlinear transformation, then this feature of the derivative being a tensor will not be true. So that in the case of if you go to more advanced subject on general relativity, the derivative of a tensor will not be a tensor. So you have to remember that, so that in this particular case, it's just a special case of the special relativity. Right, so let me see how can we apply this idea of a derivative being a tensor in special relativity. Well, one of the things that we want to do is to look at derivatives of, say, a vector field. Okay, in this case, let's consider the vector field to be J mu here. And remember, we can take the derivative in such a way that it's being contracted here. So generally, one takes the derivative in this form. Okay. So here is just you have both being free index, but over here you can see I can take this to be the same index, top and bottom. Okay, and this is what we call a four divergence. It's analog of, say, del dot, say, v, for example, divergence of v. Okay, so now in the four-dimensional case, it's given by this form, and if you look what that is, it's simply just you just take all possible components and then you just sum it. So in other words, you have your spatial part, which is d dx I, j I running 1 to 3, okay, and then the other part is d dx4, j4. Please do not get confused whether this one should be a minus sign. In this case, we're just summing everything directly without any consideration of minus sign. Okay, so here you just simply, this is just like writing down all possible derivatives in this form. And there's no minus sign. Okay. So, and what that corresponds to? Well, in this part, the spatial part is just your divergence in 3D. Okay. So I can write this as delta nebula dot j plus what is ddx4 here is remember we have to make it dimensionally correct, so you have 1 over c ddt j4. Okay, now why is this important for us is when we look at some special cases, like when j mu itself is given by a derivative of scalar. Okay, here's an example over here. What happens in this particular case? Here I'm using again this particular notation now, which is partial mu, which partial mu here is partial x mu, partial mu on top is partial x mu at the bottom. Okay, so this is just rewriting in this particular notation. Okay, so I have partial mu which is given by that. Okay, and then I just simply plug into this divergence over here, and I will be able to get again the same kind of thing happening over here, reappearing here. So this is your ji now, and this is your j4. Okay, and what happens in this particular case, you get your Laplacian. So this is just, remember, del dot del phi, and then you have this what I call derivative of with respect to time. And remember that in this particular case, okay, this is your xyz, for example, and then this is ct. This for the contravariant case. When you do a covariant case, this fourth component gets a negative sign. Okay, remember what we do is essentially x mu here is eta mu x mu. Okay, so you can actually show that this is that. Okay. So essentially with this, your initially it's just a normal summation. Because of this component over here of your covariant case, it requires a minus sign, and then this becomes a minus sign. Okay, so you have your Laplacian acting on your phi plus the second order time derivative multiplied by 1 over c squared acting on phi, and this is essentially you remember this appears as a wave equation. Okay, if this is actually equals to 0, okay, this is actually equal to 0, then essentially this is a wave equation of what? Of some function that travels at the speed of light. Okay, so as you can see now, I can think of this as describing the example would be the plane wave of a electromagnetic wave. Okay, We also introduced the idea of Lambertian. Okay. Lambertian is given by this symbol. Okay, this we call just a square. Okay, which correspond to this taking the derivative contracted in this sense. Okay, partial mu, partial mu. Okay, now so in other words, your wave equation can be written in terms of the D'Alembert thing, just like it's a four-dimensional version of your, say, your Poisson equation. So this is a Poisson equation. So your wave equation is essentially that. So this is wave equation. So it's a generalization of this. The other thing that one should also note that if you have this divergence, for example, to be equal to 0, what's going to happen is I can just simply write down the summation of this mu and mu here. So I just get that. But what is this? If I write your j to be equals to this vector here, j mu equals to the three-dimensional vector j, and then this fourth component for the time being we'll just write as 0. Okay, we will explain this physically what this means. Then what's going to happen, this equation over here becomes this equation over here. Okay, 0 multiplied by 1 over ct over here from the derivative, then that c disappears, so you're just having this equation. And this is essentially, you have seen this before many times, I believe, is the equation of continuity. Okay, and this equation of continuity actually tells you about a conservation of a quantity. So I can think, for example, your JB, so well, the one that will be relevant to us will be the electric current density, and this will be your charge density. Okay, so what does that tells us? Okay, the divergence of your electric current plus the rate of change of your charge density must be equal to 0, in the sense that if you look at what happens inside a particular volume, I think we have done this in maths method, if and usually what happens is in a particular volume you have a charge density, so this will be a charged body. But if there are what you call current in and current out from the volume of the body, so this is current J, then this can actually change the charge density here. Okay. Your charge can actually change accordingly with this influx of current and outflux of current. Okay, so that just says that if you want to have your charge density to be varying with respect to time, then there must be some current density flowing in and out. Okay. So again, the idea of this equation of continuity, as I said, is saying something about conservation. How do you actually see this in a more conventional way is to think of, for example, your charge when you integrate over the volume gives you the total charge. Okay, so if I take the total charge, take the time derivative of that, so I get ddt of this integral. Okay, so when I bring this in, this, remember that no, this will now be depending on your spatial coordinates as well, and of course in this particular case, if you have varying charges, then you have time dependent as well, so you have changed this to partial derivative, okay, because of your rho now becomes a function of x, y, z, and also t. Okay, so I get this partial rho partial t d3v, and according to this equation of continuity, I can now replace d partial rho partial t by minus of divergence of j. Okay, and so I have this integral with respect to this volume of the divergence. And then you remember in maths method we have learned about Gauss theorem or divergence theorem. Then I can convert this three-dimensional integral to a two-dimensional integral. Okay, so here will be so in this particular case, one looks at a particular element on the surface. Okay, so this will actually give you an element on the surface, and then this will be just a dot product to that element. Okay, but that tells us what? That tells us, okay, I'll be looking at how the electric current sort of no, the flux of the electric current moving in and out from that particular surface that enclose this particular volume. Okay, so that essentially gives you this. Okay, you have the total flux of charge into V per unit time. Okay, so this is just a restatement. In other words, when we use that equation of continuity here, which is d rho dt plus del dot j 0, essentially just a restatement of that. Okay, so this is there is a way to show that you can show that this in a more concrete way, how to show this as a conservation of charge by considering the four-dimensional integral instead. But I think we'll leave that to the classical fields later on. Okay, perhaps at this stage we can take a little break for a while and let me figure out that equation that sort of get confused a little bit. Shall we? Okay. So we take a break of 5 minutes. I hope everyone is back. So what I did was, okay, perhaps I should explain back this particular equation, Vk1 equals to that. Okay, this comes from, that's my, sorry, looking for my, all right. So if everyone remembers that this is actually equals to v dot k, so vk1 is v dot k, and if you use the thing that we had in terms of magnitudes, this is cos theta here, so this is okay, let me just put another step in. Your k itself can be written in terms of k, magnitude of k times the direction of the propagation, the unit vector here, cos theta, and then this will be v k and cos theta. And then remember that your k, the magnitude, is equals to omega over c, so that gives you the omega v over c cos theta. Okay, this is equals to 1. So using this, okay, vk1 equals to that, it's just a simple substitution, which I got confused a little bit just now. So I had that. So your k1 is now what? your k1 is equals to maybe I should write this k1 dash first. So k1 dash equals to omega over c cos theta. This is in terms of dash. Okay, so your k1 is omega over c cos theta. So I just simply plug in, so I get this equation over here. Oops, what's happening? Are you still there? Are you seeing this? Okay, something happened just now, I'm not sure. Uh, okay, so you have your k1 dash equals to that, okay, remember that, sorry, this one. And then your L1 dash mu k mu will give you L1 dash 1 k1, okay, so this will give you L1 dash 1 k1, and then the other ones are going to be trivial. So remember that your components for your L only exist in the first row or first column, and the fourth row and the fourth column. So this becomes L1 dash 4k4. Okay, so now I just simply substitute what L1 dash 1 is, which is gamma. Okay, so that gives you that gamma k1. Okay, but now what is k1? K1 is equals to that. Okay, then your L1 dash k4 is that. Okay, and so I can now simply use that. So gamma k1 is what? So I'm just writing down here now. Gamma k1 is gamma omega on c cos theta minus gamma v on c. K4 is omega on c. Okay, so I just simply bring out the common factor out. So this equals to gamma over omega on c cos theta minus v on c. So it was that simple. Sorry, I got confused. So that settles that. Okay. Right. So we finished this lecture 8. So we should now move on to lecture 9. So lecture 9 is about relativistic kinematics. Particularly, we are going to write down some equations with respect to velocity and acceleration. Okay, it's just like your ordinary Newtonian kinematics. You get relationship between velocity, time, position, and acceleration. Okay, so we are going to do more or less the same kind of thing, but before we can actually do that, before we can actually discuss what is velocity in the four-dimensional sense and acceleration in the four-dimensional sense, we have to make sure we can have a proper notion of the time derivative. Okay, because the time derivative will give you velocity, and the time derivative will give you the acceleration. Okay, so how can you actually do this? Because your time is part of your space-time coordinates, and space-time coordinates depends on your reference frames. So there must be some quantity that we can actually use in order for us to be able to be independent of the space-time coordinates. So this is what we're going to do. So generally what's going to happen when you have certain kind of motion by a point particle, so you will trace out a curve. Okay, so this is essentially a curve in in space-time over here. Okay, so your position of your particle will actually move with respect to some coordinates a long time here. Okay, so this is essentially a condensed version of a three-dimensional space, and this is time. So if it's a stationary, you'll see if it doesn't move with respect to certain forces, no, it's stationary, then you just simply get a vertical line. Okay, so this for it's not quite vertical there, but you know what I mean. If it doesn't change position, then essentially it will just trace out a vertical line. Okay, here is some kind of motion with respect to maybe some forces involved. But what actually happens over here, it has to somehow the tangent of this particular curve, okay, the tangent of this particular curve has to be less than the speed of light. So remember, the tangent of this curve would be the velocity, okay, and the velocity cannot be exceeding the speed of light for ordinary particles. Okay, so in other words, the inverse slope will be less than the inverse slope of this. Okay, so remember our convention here is to take c equals to 1, so this will be your c equals to 1 here, so you get your 45 degrees thing, and then this will actually give you a light cone. Okay, so at this point, this inverse slope, okay, will be let's talk about slope rather than inverse slope. The slope over here should be steeper than this slope. So in other words, the inverse slope is actually less steep. Okay. So because the way we draw the diagram, usually what we do is in ordinary dynamics kind of diagram, this is actually t, this is actually x. Okay, then your velocity will be just the slope. Okay, but in this particular case, we have your t on the vertical direction and your spatial direction is here. So essentially, this is the trace of trajectory of a particle. Okay, and it's a one-dimensional curve. One has to think this as a one-dimensional curve inside a four-dimensional space, and that one-dimensional curve must be, if it's a curve, the effective variable sort of parameterizing the curve is only one single parameter. Okay, so that this gives you this particular curve. So you can think of your space-time coordinates now is being parameterized by this lambda, so that it appears as this particular curve here. And this curve, I think I should have mentioned this. This curve is called the whirl line, okay, of that particle. So this is the whirl line. Okay, so let's go below. So this is the thing I mentioned just now. So you require the velocity to be less than c. So this one will look steeper than this one. Okay. So if one wants to have the same sense of, when you have a curve here, for example, this tangent curve represents a slope. So one should also have that kind of thing inside this particular diagram. But now you take the derivative with respect to this parameter that parameterizes this particular curve. Okay, so let's do that, and we require that derivative with respect to that parameter to be time-like, because we want it to be less than the speed of light. Okay, so that appears inside this particular cone, and we can actually check this by taking the product together with this Minkowski metric. So remember, for example, over here, ds squared equals to eta mu nu dx mu dx nu. So this tells you about a four-dimensional interval. So if I want to see that this is having a magnitude less than c, so I again use this kind of what you call contraction between the Minkowski metric with your vectors here. So here's a vector given by this derivative with respect to the parameter here. Okay, so let's do that and see what you get. So if we just simply expand the summation convention with respect to mu and nu, so I have my spatial derivative, spatial components with respect to this parameter. So dxi, d lambda square, because you have two of this object, and remember this is only diagonal, so that means mu must be equals to nu. So I have this dxi d lambda squared sum from 1 to 3. Okay, and then you have the fourth term. The fourth term, you have eta for 4. Okay, eta for 4 is -1, so that gives you this -1. Okay, and you have the derivative of your fourth coordinate with respect to lambda square. Okay, but since we do not know what this lambda is supposed to be, so what we can actually try to do is to convert this to your time coordinate. So what we do here, essentially we use a chain rule. Okay. d lambda dt. Okay. So in other words, we have this quantity multiplying this derivative on all terms, okay, and then you square it. So I can bring that common factor out, dt over d lambda squared, and then this one becomes now the derivative with respect to t, which we now know, okay, I can relate to this because this is now a derivative with respect to time. This will be the velocity, okay, vi squared over here. And what x4 is simply ct, and essentially you differentiate with respect to t, then you just give you c squared. Okay, so what is the sum of the component of the velocity square? Is just the magnitude, v squared. Okay, so you get v squared minus c squared, and since v must be less than c, then this thing is going to be less than 0. And remember our classification of the vectors. Let's say you have eta mu nu. What's the symbol I used? I can't remember previously, but never mind. A mu, a nu. So you have these three different classification. So if it's space-like, then this is greater than 0. This is space-like. If it's equal to 0, then you have your light-like. So this behaves like your light, for example. Then less than 0 will be time-like. Okay, so this is essentially a time-like vector, which is what we want. Okay. Okay. With this also, then you can see what we're trying to do over here. So we go back to this interval squared in 4 dimension, and this is given by that. And now I can simply divide this by dt and then multiply by dt. So it just simply cancel out. But what happens in this particular case, then you have this to be the derivative with respect to t, and then you get essentially the same thing here. Okay, just like over here. But over here, we do not know what this is yet. Okay, so what's the significance of this is the fact that your four-dimensional interval squared is a scalar, and it's invariant under change of change of reference frames. So this negative quantity is a scalar, and it doesn't change. When you change reference frames. So I can set that to be as a parameter that parameterize your curve previously, because it's something that doesn't change with respect to change of coordinates. So I'm going to set this thing that negative. So now we take this ds squared, okay, but ds squared is negative, okay. So I'm putting a minus sign here, so that becomes positive, and then this is actually the what you call a square. So I take the square root, okay, and then I'll multiply it by 1 over c, so that remember that this is the dimension of this, essentially the dimension of length, and then when we divide it by the dimension of, with the velocity of light, it gives you the dimension of time. Okay, so this dimension of this quantity tau here is carrying the dimension of time. Okay, and the good thing about this object, or this quantity, which now carries the dimension of time, is invariant under change of reference because it comes from this ds squared. Okay, and ds squared, remember, it doesn't change under change of reference frames. So in other words, this d tau doesn't change under change of reference frame. So we can use this as your parameter to parameterize your curve earlier. Okay, so this now we can actually think of replacing this lambda by tau, and you get what you need essentially. And the relationship between this sort of variable tau, which has the dimension of dimension of time, with the time coordinate is just given by this. Okay, so this is coming from taking this quantity here. Okay, so I'm taking now minus ds squared to be c squared minus v squared dt squared, sorry. Okay, and dividing it by dt, okay, then I will be able to get so what do I need? I'll bring out 1 over c. So I'll bring out 1 over c. Oh, no, that, so this I bring out c, so this will give you 1 minus v on c squared, sorry, 1 on minus v squared on c squared dt squared. Okay, so I bring out the factor of dt squared outside the square root, so it becomes dt, and this becomes 1 square root of 1 minus v squared on c squared, which is that, and this c squared coming out from the square root, okay, will give you c, multiplied by 1 over c over here, then we actually have this quantity. Okay. So all right. So this is essentially a factor that you have seen before, where gamma equals to 1 on square root 1 minus v squared on c squared. So in other words, this is 1 over gamma times dt. So in other words, the parameter tau relates to your time coordinate by just this factor of the reciprocal of your relativistic factor. Okay. So we can use this to parameterize your curve, and then we can actually start defining things with respect to this tau parameter. And one of the convenient thing that one can actually, this is again trying to give you a sense of what this tau is supposed to be. If you go to an inertial frame so that your particle is actually at rest or momentarily at rest because it's actually moving, then your what happened in this particular case, then your v dash is going to be say 0 here because it's momentary at rest, and then your derivative with respect to time, so the fourth component, derivative with respect to time will give you c, okay, and then essentially you get that. So this is what we call a co-moving frame. Excuse me, okay, sorry about that interruption. Where were we? Okay, so if you think of this particle sort of you have a frame sort of attached to it along with the motion. Okay, so in other words, in the reference frame of this co-moving frame, okay, that moves together with the particle is essentially stationary. Okay, so when it's stationary, then you have your velocity to be equal to 0, and then your time is just given by this component c there. Okay, sorry, your okay. I should say that your x mu will be 0 and c. Okay, so that means it stays at the origin because you're carrying the frame together with the particle. Okay, so when you take the derivative with respect to time in that frame, then this becomes 0 vector and c. Or you can actually have a different fixed coordinates here. Okay, so essentially we normally consider this idea of proper frame to help us analyze kinematics inside this moving particle. So in this particular case, if you look at what actually happened over here, if you just consider the proper frame or the co-moving frame, so your v squared is now replaced by 0 here, okay? And then essentially this will be just minus c squared dt squared, okay, which is related to your proper this coordinate that this parameter that we actually mentioned before, which is now what we call the proper time, because it is related to this time coordinate inside your proper co-moving frame. Okay, so I'm not explaining this well, but essentially this gives you the interpretation of the tau parameter that we've seen earlier, which is essentially just like a time parameter that sort of moves along together with the particle. Okay, so this is the tau will be the a clock moving together with the particle. So and you have to remember that this tau, whatever the reference frame is supposed to be, it's going to be fixed because it comes from your ds squared. Okay, so one can start thinking of, okay, now I can start to mention what is the total time taken by a particle to move along the curve. So I can just simply say, for example, here you have your curve just now. So here's a point A, here's a point B. I can start to sort of give you a measure of time between this point A and B by just considering the integral of the tau, which is the time measured by the particle itself, going from that event A to event B. But I can now, this essentially is the co-moving frame. But I can now retranslate this to any frame, because I can simply take your d tau here in terms of chain rule. You get d tau over dt times dt, and d tau over dt is essentially 1 over gamma. You have seen this earlier. Okay, and I can rewrite this as the time measured by some frame. Okay, but it relates to the time measured by the what you call by the particle itself. So irrespective who's measuring it, I can always compare with the clock that is actually moving together with the particle. Okay, so here will be with respect to a certain frame, but essentially that quantity given that it's multiplied by this factor will give you the proper time. Okay, I hope that makes sense. I'm not sure if I explain it correctly. So here what one can actually try to do, can start thinking of your tau. So here if I fix this part and make this thing to be a variable, okay, then I can think of this tau as a function of the coordinate time t, okay, when tb is actually replaced by t. So I have now the proper time written as a function of your coordinate time. So once you have this kind of parameter tau, one can start to do all the kind of kinematical variables that we want, for example. So let's look at the kinematical variables that were mentioned earlier. The things that we normally want is the velocity. The displacement can be given by your space-time coordinates. Okay, so you have the velocity, and also the other thing that we want for your kinematical variables is your acceleration. Okay, So let's do that by defining the tangent vector to the line. Remember, is given earlier in terms of the x mu d lambda, where lambda is sort of parameterized along the curve, right? So this is actually d lambda, for example, here. Now we replace this d lambda equals to your d tau. Okay, so in other words, the tangent vector is now given by the derivative of your space-time coordinates with respect to this parameter tau, which actually gives you the tangent vector. Okay, and we define this as the velocity 4 vector, or the 4 velocity. Okay, and as you can see, this is actually an object, this quantity, this 4 velocity, is an object with an index on top. So if this is a proper vector, then it should have the right transformation law. And you can actually do this. You can actually do this by considering that under Lorentz, some Lorentz transformation for the coordinates, your d tau doesn't change because d tau is related to your square root minus ds squared. Okay, so this is scalar. Okay, so in other words, d tau doesn't change. That means d tau equals to d tau dash. So if you convert this to the dash coordinate from this formula, so I get v mu dash dx mu dash d tau dash, and d tau dash is equal to d tau. So I just simply have dx mu dash over d tau. But x mu dash, we know this is already a 4 vector. Okay, so the position vector, this is a contravariant 4 vector. And you know how this transform according to your Lorentz matrix. Okay, so I have this multiplied by this Lorentz matrix, and then I'll be changing this mu dash into a nu. But what is this now? Well, this is essentially your original 4 velocity. So the 4 velocity here in the dash coordinate is related to the 4 velocity here in the dash coordinate by just a Lorentz transformation, and that tells us that this is the 4 vector. Okay, so this is fine. We would like to see what are this object in terms of components. Okay, so again, what do? We just use the chain rule and refer back to the time coordinate itself. So this becomes d tau, dt over d tau, and then this will be dx mu dt. So this will be easy for us to interpret in terms of the time coordinates with respect to a particular frame. So this will be d dt of x ct. Okay, so you take the derivative of x, will give you the velocity v, the ordinary velocity v. Okay, and then ct differentiated with respect to t is just c. So in other words, this will be your components for your v mu. Okay, the 4 velocity. So components of 4 velocity is just, remember, it's not just v, it's gamma v, gamma c. Okay, and the other thing that is good to know is what is this magnitude, so to speak, of this 4 velocity. So to deal with magnitude, you remember, you just need to form a scalar, and you can form a scalar by just what you call contracting your contravariant contravariant vector with its covariant vector. Okay, and this actually gives you this. Okay, so remember, if this is your components for your contravariant case, so this is v mu here, so v mu here, you just use your metric tensor to lower down the indices, and this will become gamma v minus gamma c. Okay, so you take the product of this thing, so you get gamma squared multiplied by v squared minus c squared, and gamma squared is 1 over 1 minus v squared on c squared. Okay, and then you can simplify this, and this equals to minus c squared, which is good because remember, this is a scalar. Okay, and you expect scalar doesn't change under change of reference frame, and c squared is a scalar. Your speed of light doesn't change in any frame. Okay, it remains c. So this is good. Okay, one can also see the same fact by just using the definition of your v mu earlier with respect to the proper time, and then you get again the same what you call the same result. Okay, so now essentially we have defined a four velocity in almost the same sense like your velocity in the ordinary Newtonian mechanics. The only difference is what is actually measured with respect to this proper time. Okay, so this is the thing that we will have. Okay, and also the other thing that we see over here, when we take the contraction, this gives you a minus c squared, and that's a negative, and that means that your four velocity here is actually a time-like vector. Okay, so I think I want to, let me see what do we have next. Okay. Probably I will stop after the 4 acceleration, okay, because I need to do something else. So once you have defined a 4 velocity with respect to the proper time, then it's quite easy to generalize this to, say, acceleration. So you just take the 4 velocity, take the derivative with respect to the proper time, and we define this as the 4 acceleration or acceleration 4 vector. Okay, and you can check for yourself that this is again transforms like a proper vector using the Lorentz transformation. Okay, so I want to do that here. It's just, you can see it's obvious because this is already a 4 vector, and this is this is scalar, so that means a mu must be a 4 vector. But what is this 4 acceleration is? Okay, again we want to see what are the components inside this. So we can always try to use the chain rule to convert this derivative with respect to the proper time to a derivative with respect to the coordinate time. So again, dt d tau times dt d dt. Okay, so dt d tau is gamma, and d dt will operate on this components of v mu, and components of v mu is what? Is gamma v and gamma c. Okay, remember that earlier. So gamma is constant with respect to time. Okay, and then this you can just get back to this. Oh, sorry. I should not say that because your gamma here is actually with respect to, remember we are changing it to we are changing this in the proper frame, co-moving frame. Okay, so your co-moving frame, one has to remember your co-moving frame might be a frame which is accelerating. So one has to be careful about that. Okay. So over here we will take that for a moment. That means we have to take the derivative of gamma as well. So I have d gamma dt times v, and then gamma times dv dt. Okay. And over here again the same thing. You get d gamma dt times c, and then gamma times dc dt, but c is constant, so that gives you just c d gamma dt. Okay, so this would be the components of your forward acceleration in a particular reference frame. Okay, so you have this, but let's put it into the proper frame and see what happens. In the proper frame, your gamma equals to 1, okay, because of v equals 0. And d gamma dt, gamma is, remember, is, what am I doing here? I think this is a mistake. I should be doing this. Maybe this 1 minus v on c squared equals to 1. So gamma would be 1 on square root 1 minus v squared on c squared, and that still equals to 1. Okay, I should be careful with that. Okay. So this is actually wrong. So now d gamma dt is the derivative of this factor here. Okay, so I will have to differentiate that. Sorry about that. The only term that can change with time. Remember that this v is your the velocity of the particle. Okay, and in this particular case, velocity of the particle in the proper frame. Okay, so that can change with respect to time. So I have dv dt, and then I differentiate that, so I will have minus half. Okay. Again, this is just chain rule. Okay, you can check it out later on. So I will have minus half there, and then differentiate inside this term. Remember, minus half, and then I have minus 1 on this exponent here, so that gives you that. Okay, and then I differentiate your v inside here, so that gives you minus 2v on c squared. Okay, so given that, now you can look at this, and if you're looking at your v in the proper frame, then this thing goes to 0. Okay, so in other words, in the proper frame, your forward acceleration is just your ordinary acceleration. Okay. And then of course the fourth component, remember what's the fourth component? Your fourth component is just c d gamma dt, and d gamma dt, we have actually shown this to be equal to 0 in the proper frame. Okay, so in other words, in the proper frame, this is just like your ordinary acceleration. Okay, but one has to remember this is not the frame of an inertial frame. So in an inertial frame, you have to go back to this original quantity, okay, and work out what all this is. Okay. So as I said, now once you know this as a 4 vector for acceleration with respect to the proper time, okay, one would also like to see what is the magnitude of this. Okay, so magnitude, you just remember, you just take your a mu, contract with this a mu, the covariant case. So covariant case is now, it's quite easy now. in the proper frame, okay, in proper frame, this will be just A, and usually we replace the fourth component by a minus sign, but minus 0 is just 0. Okay, so you get essentially A squared, and A squared is a positive quantity, so that gives you a greater than 0 quantity. So in other words, your A mu is really a space-like quantity, space-like vector, sorry. And one of the things that one can actually prove, probably this will be given as a general, what you call, rule. Okay, a general rule is that when you contract a space-like vector with a time-like vector, you always get 0. I should check that. Sorry about this. So it's quite easy when you do this in a proper frame, because in proper frame you know what the components are. So here is A0. Excuse me, somebody. Okay, so your components of A are given by A0, and components for V is given in the proper frame is given by that. So you can just simply take the product, and then you can actually see that your contraction of your 4 acceleration with the 4 velocity is just equal to 0. Okay, and this confirms what I said earlier. You take the space-like vector and time-like vector, it gets you quantity. Okay, so this is an alternative way of looking at it. So you have A mu, V mu, but A mu is what? A mu is essentially the V mu, the tau. Okay, so you get that, and this you can use your metric tensor to raise this index up. Okay, and then this one, as you have seen earlier, okay, I'm bringing out this you can sort of replace this by the tau, or I can actually replace it by a half if I want to, but never mind. So I can replace this like by the total derivative, but I have to minus the other derivative. Okay, so the total derivative, you can see that this is actually equals to the inner product of your v's, which is actually gives you minus c squared before. So d tau minus c squared is going to be 0, and then I have this, but this is actually equivalent to that one, and essentially you can bring it on the other side. Then this tells us, okay, your A mu V mu equals 0. I think I would like to stop here if you don't mind, because I have something to do. So let me go back to you. So let me get your attendance first before finishing. Okay. So is it okay for me to stop now? Otherwise, I can still continue, but I have to rush for other things. So can we stop now? So I hope you have sent in all your assignments. So if you have not done so, please do so now. It's still open, because I've forgotten to unshare the folder last night. So I'll give you until 12 noon, but we have already done it, so I will just unshare the folder later on. Okay, so thank you everyone.